Welcome to MEI Mechanics. We're on the topic of forces and moments, and this is video 1.3, equilibrium of a rigid body. Now, we introduced rigid bodies in a previous video, and this rigid body might be subject to several forces, different sizes, different directions, acting at different points. But if we find that that object is not accelerating and not rotating, then that's static equilibrium, and two things must be true. The resultant force in any direction must equal 0, so the sum of all those forces must be 0, as we already know, but also the total moment of all the forces about any point must equal 0. Otherwise this thing would start to rotate. So what that means is that we can write down three equations, alright, because we have the two dimensions, horizontal and vertical, or possibly two perpendicular directions aligned with a plane. But either way, we've got two directions that we can resolve the forces in, plus the equation that we get from considering moments. So the sort of things that we could do is to resolve in two directions and take moments about 1 point, or we could just resolve in one direction but take moments about 2 points. Or we could take moments about 3 points. Alright, as long as they're not on the same line, then that will give us all the information that we need. Alright, now when we're choosing points to take moments about, we need to be careful, because often we can make life a lot easier for ourselves by choosing points at which certain forces are actually acting, because if you pick your point to be a point where there's a force acting, then that force itself has 0 moment about that point, and that simplifies the expression that you get. So let's have a look at an example. We have a uniform rod, mass 5 kilograms, length 3 meters, and it's freely hinged to a vertical wall at A. Now, firstly, it's worth just saying what we mean by freely hinged. What that means is that that rod is free to rotate about this hinge here, and this hinge is frictionless, so we don't need to worry about any turning effect on the rod from that point at all. We just assume that that rod can freely rotate in accordance to what other forces are acting about that point. Okay, and it's held in equilibrium, so that means that those things we mentioned earlier are all going to be true. 0 total force and 0 total moment about any point. And it's being held in place by a cable which is making an angle of 40 degrees to the rod. And the first thing that we want to calculate is the tension in the cable. So there'll be a tension acting on B, acting in the direction of this cable. So let's call this the tension T, and what we're going to want to do is to resolve that tension in these two different directions. Okay, so that angle there will be 40 degrees. So here we'll have T sine 40 degrees. And then going this way, we'll have T cos 40 degrees. There will also be the weight of the rod. Now, we're told it's a uniform rod, so its centre of mass will be in the middle, and that weight will be acting down like that. Mass is 5, so the weight is 5g. And because the rod has a length of 3 meters, it means that this distance here will be 1.5 meters, and that's going to be important later when we think about turning moments. So, to find the tension in the cable, all we're going to need to do is take turning moments about A. Okay, so let's do that. So starting with the anti-clockwise one, well, we have this perpendicular component, T sine 40. So we'll write that in T sine 40, and that needs to be multiplied by the whole of that distance, which we know is 3 meters, and then acting in the clockwise manner, we have this force of 5G. Because that's clockwise, we're going to subtract it, multiplied by its distance from that pivot, which is 1.5. Okay, and so we can rearrange that for t. Now the next part of the question asks us to find the reaction force at the hinge. Now this is an interesting one because this force could be acting in any direction really. So there'll be a force acting, a reaction force on the rod at A, but what we'll do is we'll give it two vector components, so an x component and a y component, which we'll call x and y. Okay, and we'll have to separately consider what those two components are. Alright, now remember what other forces are acting. We've still got this T acting that way, and that is split into a horizontal component and a vertical component, and obviously we still have the weight, 5G. Alright, so if we resolve horizontally, then we have this component x acting to the right, and we'll have a component of t acting to the left. Alright, so that will be t cos 40. And that must equal 0. And then we know what the value of t is from the previous part, so I can easily rearrange that to find the x newtons. And then if we do the same thing vertically, we have the component y acting upwards, plus the component of t sine 40 acting upwards, and we've got the weight acting downwards, so that's minus 5G, and that also equals 0. And if I rearrange that for y, newtons. Alright, and what we might want to do then is find the total reaction force. Now we know the individual x and y components, so the total magnitude is can be found by Pythagoras. Okay, so this total value of r will be the square root of x squared plus y squared. And if we work that out, we get a value of 38.1 newtons. Now in this second example, it's a little bit more complicated because it's a non-uniform rod. So it's got a mass of 5 kilograms, length 3 meters, but what we are told is that the center of mass of this rod is located 2 meters from A. So that's going to be roughly there. So that's where the weight of the rod is effectively going to be acting. So we've got 5G force there, which is a distance of 2 meters away. But of course, at some point we're going to need to think about the component of the 5G, or think about the if I think about that, what was method 1 earlier, think about this distance here, this perpendicular distance, which will be 2 sine 60. That's that distance. So that's the distance that we're going to be using along with this 5G to work out the moment of that force. T is acting perpendicular to the rod, so we don't need to worry about any components there when it comes to working out the moment. So if we take anti-clockwise moments about A, we have t times 3, and then clockwise minus 5g times 2 sine 60. That has to equal 0, and if I rearrange that for t, then I find that t is equal to 28.3 newtons. So that concludes video 1.3, equilibrium of a rigid body. The next video, 1.4, will be on the subject of ladders.